Okay, so hello everyone and welcome back to the second part of our control lecture today. Where did we stop? We talked about the first actual controller, right? So we introduced the bang bang controller, which basically what it does is it takes your control error and it converts that continuous control error, right? Can be anything, to basically only two outputs, either on and or off, right? It would be the most simplistic one. Technically, you can have two values, right? So most commonly known is this controller, as I said, for when you use your oven, a boiler or something. You really just say the controller turns your oven on, the heater in your oven on to get up to temperature, and then turns it off again. You see that usually when the light switches on and off. So when you make a pizza today, you can think of the control algorithm in your oven and what you have learned. Okay, so again, it's a very highly nonlinear controller because it does basically a switching between two states, right? So for aircraft or cars, this is not really what we want. We want to have a continuous controller, a linear controller, where we say, okay, if the control error is a certain value and this value is doubled, there should be a relation on the output side as well. And this is what a linear controller is doing. Okay, so this afternoon, we're going to talk about a linear controller, and actually the rest of the semester, all our controller and control systems will be linear. But I usually like to introduce the bang bang controller because everybody uses it, and I think it's pretty a nice introduction to that. Okay, for the linear controller, we're going to talk about the famous PID controller, and today then we're going to talk about how can we actually analyze a closed loop system, right? And there we are basically going back to the block diagrams, which I guess you all love very much. Okay, so let's hop over. So we said next stop, so to say, linear time invariant controllers. Okay, so because we are now back in linear system theory, we are basically allowed to write here G of S and R of S, right? This is a small but important detail. If your system is non-linear, there's actually no Laplace domain. You are not allowed to write transfer function as soon as you have a non-linear system. So, because we are now restricting us to linear systems and linear controllers, we are allowed to write the full loop here in the Laplace domain, right? And you know, because it's in the Laplace domain, we can simply solve that loop as we have done a couple of lectures ago by multiplying blocks together and adding feedback loops. So why R? Well, R simply because if you read the literature, you might find instead of controller also regulator instead. And we will use the C on a different point. That's why. So important really to note here is that this system here, this is a piece of hardware, right? This is your car, your aircraft, whatever you like. While this thing here is basically an artificial system, which you most of the time are going to put on a microcontroller, right? So you are freely to choose this R. It's not given, right? It's your responsibility as a control design engineer to choose the controller and make the closed loop system, right, behave as you want. While this is given, right, the system, you cannot per se not change that. I mean, you can change it, but you need to do a reconstruction, right? You can change your aerodynamic coefficient of your aircraft if you change the wing. Yes, but usually you will consider that as given because some smart people in the design department will have thought about this. this R here, you're free to choose, right? So this is no piece of, actually it is a piece of hardware because you need to put it on a computer, which you stuck into your system. But technically, this is a piece of computer software, so to say, right? Okay. So next thing we're going to talk about here, if I say you can arbitrarily choose that R of S, this is kind of huge, right? Because you can put any transfer function in there, what you like. But this is obviously too big of a problem, right? So this is why we're going to restrict ourselves to a certain kind of transfer function, a PID transfer function, what the controller looks like. And this is why PID controllers are named PID, because the transfer function has a proportional part, an integrating part, and a differentiating part. This is why a PID controller is PID controller, right? So we're already restricting ourselves to only basically 3 elements the controller can have. And why it is the case, we will learn that today and in the next lectures. Okay, so this controller, this R of S, we will use a PID controller. And as the name implies, the PID controller has a proportional part, an integral part, and a differentiating part. Okay, so what is a controller doing? It's basically taking your control error, right, and generating an input to your system, right? Remember, our system, G of S, has the input U and the output Y. And now we want to design this artificial system here, R of S, which has as input our control error and as output our control command, which then goes to our system. Okay, so if we only want to consider this for now, we're going to use a PID controller for that. Okay, so PID is pretty straightforward, so let's write down the time domain equation here for our PID control system. Our output of the controller is the control input to the system, so it's U of t. We don't have any t here, right? So it's not t1, t2, so we don't have any derivatives of u. On the right-hand side, we have a proportional part, named that kp, times our control error. We have an integral part, so we say, okay, integral over 0 to t of our control error, and we need to change the variable here, right? And we have an integral gain as well. And finally, we have a differentiating part, right? So we have some gain here times d over dt of our control error. This is a form a PID controller looks like in a parallel structure. Why it's named parallel structure, I'll come to that in a minute. So you easily can Laplace transform this. So if you take that and make a Laplace transform, it's bad today. Okay, I mean, you know how to replace all of this, and what the result is. R of S is nothing but the output over your input, which in case of the PID controller is your, obviously. The input is the control error, the output is your input to the system, and then Kp times E of t, Laplace transformed, is simply Kp, plus the integral here is 1 over S, so it's Ki over S, and this guy here is Kd times S, right? Because we have E dot here. This Laplace transformed is S times E of S. So this is the transfer. It's not really a transfer function yet, right? Because we have basically 3 transfer functions, if you so want to say that. Because this is a transfer function, this one, and this one. So we will make that simpler in a second. Okay. So if you would draw the block diagram of this guy, you would end up here, right? So your control arrow comes in, it runs through a proportional channel, an integral channel, and a differentiating channel, and at the end it's summed up again at this summation here. And this is why this form, or the PID controller, this PID controller form is called parallel structure, because if you draw the block diagram, all these blocks are in parallel, right? Like you know it from electrical engineering. Okay. So this parallel form is usually not really convenient to work with, right? This is why we actually going to transform this in a single transfer function, right? So how would you do this? Oops, sorry. How would you do this? Compute a single transfer function R of S, meaning that we have a single numerator and a single denominator. Simply bring it on the same denominator, right? This is what's going to happen on the next slide. If you bring that parallel structure into on the same denominator, which is basically S, right? So you need to multiply here Kp times S, and you multiply this guy by S. You have Kd S squared plus Ki plus Kp times S over S. And now this guy is called the series structure of a PID controller. Why series structure? Because it's a simple transfer function. Look at the block diagram, it's just one piece, right? So all the elements are in series, so to say. Okay. Okay. So this series structure of the PID controller obviously corresponds to the polynomial form of a transfer function. Polynomial form, right? In literature, it's just named series structure, specifically indicating that it is a PID controller, right? It's just a PID controller has a series structure and a parallel structure, and the series structure is equivalent to the polynomial form, right? So we have a second order polynomial here. So you have two zeros, and you have one pole at 0, right? Okay. So what's next? Obviously, what I have started out, we kicked out of the day in the morning. We know that if there's a polynomial form of our controller, we also have a pole 0 form and a time constant form, right? And this is why I kind of took some time in the morning that you understand all these different forms, because the PID controller can have different forms, but basically it really doesn't matter which form you take. The form you take should come from the system form you have. So obviously you can bring every system in a different form and then use the controller form you like. But usually if the system comes along with a pole 0 form, take your controller in the pole 0 form, because you might can immediately cancel poles and zeros, right? So okay. Okay, so the pole 0 form of this guy. Let's get rid of this. Looks the following. Let's change the color. We have a gain, right? We have two zeros, and we still have this one pole at 0. If you draw the block diagram, it looks like this, right? So, yeah. One important thing here, and this is often kind of mistaken. Obviously, you can compute these zeros here from the gains here, right? So there's a connection between the gains, these guys here, and the two zeros and your controller gain, right? Bottom line is you always have three free parameters. In the first form, you are free to choose the proportional gain, the integral gain, and the differentiating gain. In the second form, you can choose 2 zeros and 1 gain, right? At the end of the day, sometimes you need to compute your Kp, Ki, and Kd from the 2 zeros you have. Most of the time you need that when you do the implementation, because when you code that in on your microcontroller, usually the series structure form or the parallel form are a little bit easier to implement, because you don't have this, especially in the parallel form, you don't have this s squared there. And a microcontroller doesn't know what a s squared is, so it's basically a derivative, so you need to approximate this with a time derivative. But actually, there you don't need to think much about the connection between one form or the other, right? As I said, if your system comes in the pole zero form, you take the PID controller in the pole zero form and you define the zeros and the gain. It doesn't matter how Kp, Ki, and Kd looks like, because you are free to choose anyway, right? And this is why, or this is not why, but we have a search form, which is obviously the time constant form, which looks like this, right? So you choose two time constants and this gain here. So why did I, and here is the first time I'm using this K star. It's because I'm not allowed to write K0 here, because the static gain of this guy here is infinite, right? Because if you let S go to 0, your steady state value will go to infinite. This is why I'm writing K star here, because we have this free integrator, but it should not kind of disturb you at this point. So bottom line is, if you choose that form, you can choose the 3 gains. If you choose the second form, the polynomial form, you can choose 2 zeros and a gain. And if you choose the time constant form, you're basically free to choose the 2 time constant and this gain and the gain here. Obviously, there is always a connection. You can always define your controller in the time constant form and then compute the pole zero form. But you are rarely going to do that. Why? Because if you need the pole zero form, you directly can use the pole zero form, right? This is why I said it's important for me to understand that you understand that there are these different forms, but the control system, right? This is not, it's free to choose anyway. It's not like an aircraft with fixed parameters. As the controller can be freely chosen by you, that means the structure can be freely chosen and the parameters. So choose the structure as it fits to your problem and not the other way around. Okay? I think that will get kind of clear when we do then some examples. Okay. One thing you might see here, or one problem here, this PID controller is not causal, right? So it's actually not realizable because we have more zeros than poles. Well, here you see it. We have a second order polynomial in the numerator and a first order polynomial in the denominator. So this controller is not, you cannot build this controller, you cannot code this controller, and this is why this controller is called the ideal PID controller. So you could say, well, what the heck, why do we use that controller then? Well, we use the PID controller because it's very easy to work with it, right? Although we always have to bear in mind that we are actually not able to implement this, but we will have a very simple trick to make it implementable and make it causal, right? Okay. So here's some more details if you want to read that at the end. This is basically says that you don't need to, or it makes sense to use the controller in the form what you prefer. So to make that controller now realizable, we are introducing some parasitic delay or parasitic lag. Well, lag, I think here is the better phrase. Yeah. So that means we simply take our controller and multiply a PD1 system to it, right? So if you look at the parallel structure of the controller, I told you we have 3 transfer functions. The first one is Kp. This is fine. Ki over S is fine too. However, the problem is this differentiating term, and I told you there are no pure differentiating system, right? Remember in the time domain when we introduced differentiating system, this D element, that didn't exist. And this is also the problem for the PID controller because it has this pure D element here, right? But I told you, instead of a pure D system, you can use a DT1, right? You can simply lag this system a little bit, right? And this now, instead of a pure, actually, let's write it here. Instead of a D system, we must use a DT1 system, right? This is what it is. And how are we going to do this? We are just adding any time a time constant, this TP here, which is pretty fast. It doesn't matter, right? What means this PT1, right, term? It just means it's an eigenmotion in the controller which decays with e to the power of minus TP times t. So if we select this TP just fast enough, much faster than our system, then we don't have any problem. You don't actually recognize it, and your controller will behave like an ideal PID controller. Just you will be able to implement it, right? And again, you can do the same for if you have any other form. This is the polynomial form. The same goes for the time constant form, whatever. So I prefer to write it always in this way, right? Always this parasitic lag, always in the time constant form, because then you don't change the static gain, right? As soon as you, I mean, technically you could write a pole here, so S plus P, but then you're changing the static gain again of this whole controller. So yeah, this is how I do it. You're free to choose. So obviously, not obviously, that's it. So one thing the idea is we are just selecting that so fast that it does not influence our system. And one rule of thumb, eine Daumenregel, is if you have a PID controller and you choose those two guys, you make that TP much faster than the time constant of these two zeros here, right? So 5% of these time constants, then you will end up with a system where you don't see where this time constant does not have an influence. For example, let's do a practical example. Some of you already worked on this espresso machine, right? And if you would now design a PID controller for that espresso machine, and you know the poles of your system are, I don't remember actually, about 1 minute and I think 6 minutes. So these are the time constant. You choose this parasitic delay 10 seconds. It's much faster than the other time constants. You're fine, right? This would be like, this is already a very practical thing. For me, at this stage, it's important that you know a PID controller is an ideal view of a PID controller, because for implementation, you additionally need to add this parasitic delay. Otherwise, especially if you do a project or something and design a controller, and then you need to code it in C or on your Arduino chip, you will run into troubles when you don't consider that, because it simply will not work. Okay, so this was actually all at this point for the PID controller. Here it's important to note that, okay, the PID controller, our controller itself, is a linear system, right? This makes our life easier because our system itself, the system we are controlling, is linear. So it definitely makes sense to also choose a linear controller. But if we just say the controller can be any linear function, we have too many options, and we will see that the PID controller itself is already a good starting point. I mean, you can always go with a more complicated controller, but I think 97% of the controllers in the world are PID controllers. So this controller is already pretty powerful. For example, all flight controllers, Airbus A380, Boeing 787, in the kernel, right? In the core, not kernel, in the core, they have PID controller there. Obviously, these PID controllers change when the aircraft changes the altitude, but basically, it's only PID control elements are in there. So you even can design aircraft flight controls with PID. So you already know quite a lot at this point. Okay, so now I'm going to show you basically a kind of a story, right? So where we are, and I'm in the next 2 or 3 lectures, I always will kind of show you that story, that you know at where we are standing in understanding control systems, right? At this point, we can say, okay, we know how such a basic linear control element, the PID controller, looks like. It has proportional and integral differentiating element. Next, we want to see, okay, we have a system. Lost my mouse. Okay. What we now have is, we have this PID controller, R of S. This is going to be PID. And we have our system, right? And ultimately, we want to kind of derive what happens if we take this PID controller and close a loop around this, right? So what happens to that closed loop system? Because at the end of the day, in engineering, you're interested in what goes in and what goes out, right? So what temperature do I put in and what temperature do I get out? So to be able to analyze this, we need next to work out a methodology and where we should look at. How do we analyze the closed loop? So this is called the closed loop. Closed loop is called because we close the loop here, right? And the transfer function from R to Y, where we use the controller, close the loop, is called the closed loop system. And next we will discuss how can we actually analyze this closed loop. You will see there's not much new there. It uses a little bit of block diagrams, and we will discuss what elements do we have in the control, what signals do we have. And with this methodology to analyze the closed loop, we then can take a look what are the elements of our PID controller doing to our system. And you will see you can actually, although you have a lot of different systems, we're always taking the same controller, and you will see the effects the single elements of our PID controller is doing to all these different systems. You can categorize this, right? But to understand what these elements are doing, we need to kind of understand what should we analyze of our closed loop, right? So we next and today going to talk about how to analyze a closed loop system. And then when we understand that, we will take a look at, well, the design problem of this guy here is basically twofold. First, you have to select a structure, and then you have to select the parameters, right? So this is the ultimate goal where we want to end next week, probably. If I tell you, or your boss, not me, your boss tells you this, please design a PID design a controller for that system, you first have to think about the structure. And with structure, I mean, do you need a P, a D, and an I element? Because often only a PI is fine. Sometimes only a PD works, right? It does not mean that you always need all three elements. So you need to think about the structure of your controller. If you have the structure, you need to think about the numeric values. Okay, so this is where we're going to end up, and there are numerous methods how you can design a controller. But first, we need to understand where should we look at, what should we design for, how should the closed loop look like, and which transfer function makes sense. Obviously, the first transfer function you will see is just the input to the output, but there are more because we have now a full loop. Okay, but let's take that step by step. Okay, as I said, we now have a closed loop system consisting of a controller, of a system, something which goes in, a reference usually, something which comes out. We are building the control error. We generate the control input, and we want to know how to analyze this closed loop system, right? This is what should we do? Well, there are different possibilities. Well, the first possibility, there are not so many, there are only two. First, you could say, okay, I'm going to analyze my controller, my closed loop, so my closed loop system in the time domain, right? You could easily do this because you know how the controller looks like in the time domain, right? You can solve the ODE and then you can check for certain input signals and say, okay, but at this point you should realize that analyzing your system in the time domain might be a little bit troublesome when you need to solve that by hand. Obviously, the second option is you can do it in the Laplace domain, right? So I'm drawing all the time this nice loop, so it's maybe a good idea to analyze your closed loop in the Laplace domain. So let's talk about the time domain still a little for one or two slides. Well, you need to solve the ODE. Now it's up to you, well, it's not up to you. Most of the time you're not going to solve your ODE by hand, right? We said, okay, we can use tools like MATLAB where we put in our system and let MATLAB do the job. You did that already with the espresso machine, right? You said, okay, I'm using a numerical solver to use the ODEs. By the way, if you go back to the first lab exercise in Simulink and look now inside these elements, you will see simple transfer functions in there, right? So these are the systems. Okay, so most of the time we're gonna solve that ODE numerically using a computer-aided tool and take a look, for example, how does it respond to a step. What is interesting, where we are looking at, think back to the espresso example, you basically looked at the steady state, so at the stationary behavior. What temperature, what temperature do I reach? Where does it go to? As well as to the dynamic properties, right? So some of you wrote me an email, this is oscillating too much. I'm reaching 125 degrees before it converges to a steady state value. So you're interested in the steady state values and in the dynamical properties, right? So we know how we can analyze this for basic systems, right? And obviously, if you have a more complicated system, we still can do that as long as we solve it numerically. However, just for a quick shot, it's still a lot of work because either you need to do the manual calculation or you need to do the numerical solution, while for the numerical solution you don't need to solve it, but you need to code it before, right? So you need to build up your model like you needed to do with the espresso machine. You already had the blocks there, but you needed to build it and to reach the final correct model. So there's still some work involved, right, to bring that into your computer-aided software. This is why we're obviously going to do that in the Laplace domain, where things are much easier and we can do that on paper, right? So we don't need to think about coding it up, because we only code it up when we have already a good knowledge about our system, right? So you can see this as preliminary step. So this is why we're going to do this in the Laplace domain, because we know in the Laplace domain we can easily access stability, right? We can easily determine initial and final values for certain inputs, and we know that we only need a handful of inputs. The question now arises, what transfer functions do I take? Right? So why is this even a question, right? You could say, why is that a question? If I have an espresso machine, I put in 96 degrees, I want to know 96 degrees. transfer function from your reference to your output. I fully agree, but there are more than this. Why? When you close the loop, you now have not only one system where something goes in and something goes out, you have additionally a controller. And you might want to know, for example, what happens when you have a reference input. What's your actual control variable? So what is the output of your controller? Because, remember I told you, the controller output needs to get to it needs to be needs to go into the physical world, right? So if your computer says, please espresso machine, I need 200 watts, that might work. But if it tells you I need 2 megawatts, this is not going to work, right? So you might need also to analyze different signals in your control loop, not only the input and output. Obviously, the input to reference input to system output is the most obvious one, because this is the one you're designing for. Okay, I'm going to show you that in a control loop. So this is our control loop, and as I said a second ago, the most obvious transfer function you might want to look at is, how is my reference acting on my controlled variable, right? Think of your car. If you have a speed controller, you set your speed controller to 100 kilometers per hour. You want to check your controlled variable. Is it getting there? But you have different signals. You also could check the control error. You could say, okay, if I demand, let's take a different color here. If I demand 100 kilometers per hour, how big is my control? Is my control error overshooting? Right? So you could analyze this guy. You also could analyze, as I said before, your control input, right? Meaning that how is my reference acting on my control input to this guy? Because this signal U is the one which gets fed into my system. Think of this car example. If suddenly I'm demanding, or think of an aircraft, probably this is a better example. If you have a maximum thrust of, I don't know, 100 or 50 kilonewtons, and you plug the pilot commands something and the control input gets to 200 kilonewtons, you will have problem because you will have a problem because you have a hard limitation that because your engine cannot reach that, right? So you can use that transfer function to double check how big your control input is going to get. Not only double check, it's actually a design requirement that you probably don't command more than your actuator can do. Okay, and last but not least, what's also important, disturbances, right? How do disturbances influence our controlled variable, right? So these are the four. The first one is reference to controlled variable. The second one is reference to control error. We'll see this is pretty similar. The third one is actually the one which I talked last of. Input disturbances to controlled variable or control error. And the fourth is the reference input to the control input. So let's talk one more time about this disturbance here. What's that kind of thing? Well, a disturbance obviously most of the time acts at your input of your hardware, right? And you want to know, how does this disturbance influence my control variable? If you want to bring that back to physics, you could say in your aircraft, you want to know the aircraft is flying. Let's forget the aircraft. Let's take the car. You're driving on the highway, and your car drives automated 100 kilometers per hour. So your reference input is 100 kilometers per hour, and your controlled variable, your output, is also 100 kilometers per hour. So everything's fine. The transfer, you get what you want. What would this disturbance be? You could have headwind, backwind. Obviously, if you now say, okay, I have 20 kilometers headwind, you still want to drive 100 kilometers per hour, right? Because you don't want to drive 80 or 90 or something like this. But that's what you need to check from that transfer function. How is the disturbance acting on the controlled variable? Obviously, if you do that on your car, you're still going to drive 100 kilometers per hour because the designer did a good job in selecting the right controller. If you select the wrong controller, there might be the effect that the disturbance reduces or increases your output speed, and you need to be aware of that in the design, right? So this is what the input disturbance is, the meaning of the input disturbance. Okay, so you see we basically have four transfer functions we will take a look at, and as we are in the Laplace domain, it's actually pretty simple. We can just do block diagram algebra. Nothing new here. Basically the same things as we have done already when we introduced the block diagrams. Now, only this time we are actually talking about a closed loop control loop. Okay, so we're going to go step by step through these four transfer functions. Discuss it a little bit, and then I will have some numerical examples for the calculation. Okay, so the first transfer function I want to talk about is, I think this is the most natural one, right? How is my output of the closed loop system is going to be influenced by the reference? Same as I said, think of the espresso machine. We are demanding 96 degrees. What do we get out here, right? So, interestingly, I think I forgot about to talk about the noise here. Noise, what we are talking about, you can have not only disturbances at the output, at the input of your plant, but also at the output. Why is it called noise? Because with this noise, we are usually referring to sensor noise, right? A sensor signal will not be fully perfect. Sometimes you might have some oscillations, some high frequency noise, Rauschen. That's why we say, okay, this noise, this Rauschen, is going to enter at the output of our plant because this is the location where we put the sensor at, right? If you have your automated car driving your constant velocity, you need to measure the velocity of the car, which might not be perfect. It might be placed, I don't know, beside the engine. The engine might oscillate a little bit and transfer this oscillation onto your sensor. So your sensor signal might be a little bit noisy. This is why noise. Okay. And interestingly, the reference signal has the same channel as the noise. Take a look. There's nothing in between, just a sign change. But technically, the noise and the reference signal do go through the same channel to the control variable. And this is actually kind of a basic limitation in control. Okay, never mind. At this point, we are defining this function from the reference or the noise to the controlled variable. And this function is so important that it gets its own letter. It's called the complementary sensitivity function T of S. And this is simply defined by how our R of S, so our reference, or also our noise, N of S, transfers over to the output, right? Okay, as you now have a lot of experience in computing block diagrams, you know that we can do it the short way. We can go directly from the reference to the controlled variable. We pass through R of S times G of S, and we're going to divide this by 1 over the loop. And as we have in any recent decent control algorithm, we have a minus here. We can say it's a plus here, R of S times G of S. So when is this transfer function important? It's important to note here that this transfer function now, it's a closed loop transfer function, again has poles and zeros, but they might be different, or they will definitely going to be different from the poles and zeros of your G of S, because you wanted to change the poles. You cannot change the zeros, but you want to change the poles, right? You want to change the dynamics. Still, what are we checking here? Well, the most basic thing is you want to design a closed loop which is stable. So you will check the poles of T of S and say, okay, poles are all on the left-hand side, my system is stable, right? You might check some dynamics, but as you did with the espresso machine, hopefully, you mainly checked the steady state value, right? Do I reach my 96 degrees? How far am I off? What's the steady state gain of this transfer function? If it's 1, if the steady state gain is 1, that means my input is transferred by a gain of 1 to the output in the steady state behavior. So most of the time we check the steady state accuracy or the influence of the noise. Okay, take a sip. The second transfer function now, we are not looking at the controlled variable at the output, but not here, but we are looking at the control error, right? The inputs remain the same. So how is the reference or the noise transferred to the control error? Okay, this is also a very important transfer function, and this is why it also gets its own letter, namely S, for sensitivity function. And this sensitivity transfer function is defined as how our reference signal or our noise is transferred to our control error. Right? Okay, how does that transfer function look like? You can again do the solving of the block diagrams. If we go directly, there's just a 1 here. We go 1 over the loop, it's 1 plus R of S times G of S. Right? If that's too fast for you, please really go back and take a look at how you solve block diagrams. It should be pretty straightforward at this point. The block diagram examples which I uploaded are much more complicated than these loops with only 2 blocks, right? So why is this important, or where does actually this name sensitivity function come from? Well, we are analyzing by that function the sensitivity of our closed loop to disturbances at the control input, which is the reference and the noise, right? So you can check steady state accuracy with that transfer function. So before we go on with the other 2 remaining transfer function in that loop, we need to talk about a little bit this complementary sensitivity and sensitivity function, because they are closely linked to each other, and this is why they have the name sensitivity and complementary sensitivity, right? So if your let's go back. If your sensitivity function is 0, actually it's on the next slide, yeah. If this is 0, that means your output disturbance, the noise, is perfectly rejected, and this is why it's called sensitivity, right? If the controller is not present, so if you set R to 0, set R to 0 here, if you do this, then the sensitivity becomes 1. And now you should realize, okay, this makes sense to call it sensitivity, right? Because what a controller is basically doing, it reduces the sensitivity to noise in your system. I think it's kind of stuck here, right? At least I don't have a clear picture. I hope you do. I hope you at least can hear me. I think for the live picture, it's for the slides should be okay. So When you have no controller, you have full sensitivity to noise, right? So your system is fully influenced by that noise. By introducing a controller, you're reducing the sensitivity to noise, to disturbances in your system. This is where the sensitivity comes from. Okay, and the name complementary sensitivity simply comes from the relation that T of S plus S of S is always going to be 1. So that means if you don't have a controller, your sensitivity is 1 because you have full sensitivity to noise, and your transfer from the reference to the output is 0 because you don't have any transfer, because you have a control element which is 0. The bigger you make your gain, your controller gain, the better gets the reduction of the sensitivity and the higher becomes the complementary sensitivity. So this relation is always 1. The most easy thing is put in S equals 0 and you know what's happening in steady state. Think of the example with the espresso machine. You turned up the gain and you moved closer to this 96 degrees, but you never fully reached it. That means your sensitivity never reached a value of 0. You always remained with a little bit of sensitivity in the loop because it was the wrong controller. You need to select a different controller, but we're going to learn how we're going to do this. Okay? This is basically what I just said. Yeah. So this second discussion relates back to the fact that I told you 3 slides, let's go back, that the noise here and the reference, they share the same channel to the control variable and also to the control error. And this is really problematic. Why? Well, that's actually pretty simple. Why? Because the reference signal, you want that reference signal to show up at the output. You want your output to be 96 degrees when you put in 96 degrees. But obviously you don't want your noise showing up at the output, right? So you have a limitation there. If you make your, if you want to make your reference signal show up at the output, you're also going to make your noise show up at the output because it's the same channel, right? You cannot influence just one at this point of the lecture. We will learn later, we will introduce another degree of freedom, but at this point, this is not possible. However, it's not that dramatic because what you usually have is your input is usually slow, right? And your noise is usually pretty fast. Think of an aircraft. The pilot steers the aircraft and does this on a stick, right? So it moves it forward, it moves it back. Or think of you driving the car. I mean, let's say it's a normal car, not a race car. You drive like this, right? Or you push your gas pedal at a certain speed. This is comparably slow. A sensor noise, when you look at the sensor noise, it's pretty fast. If you take a look at, I don't know, I think you don't have a lecture on sensors, right? But actually, sensor noise is pretty fast. It's very oscillating each time step. And this is the fact where you can actually, what you can make use of. So, and remember what we said when we introduced the steady state gain and the high frequency gain. If you let S go to 0, this is your steady state transfer behavior. So what you're doing is you say, okay, you want to have T of S equal 0. You want to have T S going to 0 equal 1 and S going to 0 equals 0 for at low frequency. And for high frequency, it's the other way around. So if S goes to infinity, you want to have this guy 0 and S equal 1. What this basically means, and I think you will probably better understand it a little bit later when we are further away, is that because you know that the pilot usually is controlling the system slower than the noise is injecting, you say, okay, the controller should only work at low frequencies, and at high frequencies, I don't want to have any control action, because if I have control action there, my noise will also be show up in the beginning. So you basically do a frequency separation there. And this is really a crucial thing, which I think every second paper I review for conferences, this fails, right? And this is a problem as soon as you go to real examples. If you design a flight controller, we had a flight control design for UAV where even I forgot it. And suddenly we put the controller on, it kind of oscillated like hell because the sensor noise was amplified by the controller. You always need to make sure that there is no control action at high frequencies. And this is the reason why. Okay, so that's basically it for this discussion. I usually bring it because it's a very important practical thing, and a PID controller per se, that's the issue, does usually not ensure this if the system is not right. So sometimes it simply makes sense to adapt your PID controller to adapt it. So let me take a look at the chat. I hope it's not. Ist für die Berechnung dieser Gleichung es notwendig, diese mit S zu multiplizieren, so wie in IV und I'm not sure if I understand the question. So what we are doing here, we are just looking at the transfer function, right? I did not discuss any input signals. Obviously, if you want to do, if you say, okay, let's take this S here, and this S gives you the reference signal to the control error, right? This is the definition of this S here. And now I say, okay, my input, my reference input is a step. And you want to know how big is your control error, E, for, let's say, E of t, for t going to infinity, right? Then you again do, as you did it always, hopefully, you say, okay, I'm doing the final value. Final value theorem means S going to 0. Now I have the transfer function S of S, right? S of S. Then my input is, my reference R is a step, so R of S is equal 1 over S, multiplied by 1 over S, and then you multiply it by the S of the final value theorem. You cancel, and you solve S of S for S going to 0. This is the same as before, you just have now a closed loop transfer function, right? Or same goes if you say I have a disturbance input, which is an impulse. I want to know my output variable y or y. So what you do is you compute the transfer function from d to y, which we will see in a second is g over 1 plus g times r. And then you do the final value theorem if you want to know what happens for large t. Okay? So the final value theorem and the initial value theorem do not change just because the transfer function changed, right? It's still the same. Now I'm mainly talking about transfer function, but if you want to know how an impulse, a step, a ramp is acting in that control loop, you take the transfer function from that closed loop and you still compute the final values or initial value theorem the same as before. Hope that's clear. Actually, let me see. Yeah, this is actually in the example we're going to do after the next 5 slides. You should see that then. Okay, this is where we are. Okay, next thing we're going to talk about is the transfer function from the disturbances to our controlled variable. So basically what this guy says, how is the disturbance at the input influencing my controlled variable? So think of the aircraft example. How is my side wind, front wind, or when you think of a car, like a bump or whatever you like, how is this disturbance influencing my output? Okay, here it goes. And if you now do the transfer behavior from D to Y, D of S to Y of S, it's basically okay, let's do it one step after each other. So it's G of S over 1 plus the loop, right? R of S times G of S. And you should realize that this guy here, if you put a 1 here, this guy here is S of S. And this is why this guy, you can write it simply as G of S times S of S. Right? So it's taking your system, multiplying by the sensitivity function. And this is called disturbance sensitivity, because takes the disturbance, multiplies this by G, and then by the sensitivity function, right? And this is why it's called input disturbance sensitivity, or often just shortly disturbance sensitivity. And here, what you usually want to know, you want to compute the steady state gain and see how big is my error going to be when I have a certain disturbance. Again, the same thing. If you take a car and you say, okay, how is my disturbance influencing the output? Obviously, you need to define the disturbance, right? Often you're going to say, okay, let's say we have constant headwind. You take a step as input, right? You could also say I have a gust, right? A short wind. Then you probably take an impulse. You do the finite value theorem. Depend with the input with this S. Okay. Oops, not there yet. Last but not least, we have the channel, the number 4, which is the reference input to our control input. So, how is my reference, or the noise, but I can write noise here, influencing my control input U? And if you do that, you will realize that here now we have R of S times 1 plus R of S times G of S. And again, if you take a closer look, this guy here, is the one here, is nothing but the sensitivity S of S, and we're going to write this guy as R of S times S of S. And now again, you have the sensitivity function here. Now only this time you say my controller sensitivity, right? Why is this important? Again, this transfer function is important to judge the control activity, right? Because think of an aircraft with an aircraft, I know, with an autopilot holding speed. Again, these engine examples, you want to know how much do I demand from my engine, right? Or in the espresso machine example, how much do I demand from my heating element, right? Do I overload it? You will see that by checking the control input. Okay, so that's it. These are the 4 transfer functions here on one single slide. And what you should realize is that they all have the same denominator, right? It's always 1 plus R times G. And the only thing which is changing is the numerator. Does that make sense? Think about it. It fully makes sense, because the numerator, the denominator, which is always the same, characterizes the eigenbehavior. And this eigenbehavior of your closed loop is independent of your input, right? That's what we said. Think to the second lecture. We said on the left-hand side of our ODE, this is the eigenbehavior. It does not matter what input we have, right? This eigenbehavior is just there. It's that of our stick, right? This is the eigenbehavior. So our closed loop system has an eigenbehavior, and it should not, or it is not, this eigenbehavior, as it is eigen, is not depending on with which input it is excited, right? The input influence is in the numerator here. The eigenbehavior is the same for all. Only small difference could be if you start canceling in certain channels, right? If you say, okay, in the sensitivity you have a, in the sensitivity not, in the complementary sensitivity I have a pole zero cancellation, I cancel it out, then you're taking that eigenmode out of the equation for that function. But technically, if you don't cancel, they're all the same. Okay. Now it's a good idea to close the week, the control week, by doing some examples to get a little bit of a better idea what this means, what we just did. So we have 4 transfer functions which we are interested in the closed loop. Okay, and I'm gonna switch over to OneNote. Sorry for that, a second. Okay, so hope this is readable. And we're gonna do an example. This is a little bit big. Okay. So working with closed loop transfer function. So we have given a system G of S, which is 0.7 over S plus 1. So pretty simple, right? So it's PT1 first order system, or proportional system with a first order lag. So if you want to analyze this guy, you have a pole at -1, so it's stable, right? So that's what we like. And we have a steady state gain of 0.7. What does that actually mean? That means for a step input, we are getting only 70% of that input at the output, right? In steady state. So what do I mean with that? I mean this guy here. If you do a step input, and let's say it's 2 for the sake of not always doing a unit step input. So if this is your input and it jumps up to 2 at t equals 0, we might get an answer which is PD1, but we only getting 70%, right? So this guy only gets to 1.4 in steady state, right? It takes about 3 seconds to reach 95%, right? 3 times the time constant, which here is equal 1. Okay, so we want to improve that, and we're going to say we take that system, which is 0.7 over S plus 1, and we're gonna apply a controller around it. R of S minus here and okay. And we're gonna say, okay, our R of S is actually constant and it's gonna be 7. Okay, so just a constant gain for our controller at this point. Okay, I could write R, E, U, Y. Okay, so the question now is, what is the steady state output to a reference output of, and let's take the same here. We say our reference input R equal to, right? Okay, let's do the unit step here, but it's again here and yeah, U. So now we're gonna do here, we're gonna put in here the 2 and see what our Y is gonna be. Hopefully it's gonna get better than 1.4, otherwise, yeah, we'll see. Okay, so how would you compute that, right? So, and now here, okay, we say, now we are interested in reference to our output, okay? We know immediately that this is the complementary sensitivity. Complementary. Let's take it this way. Sensitivity T of S. Okay, and we know T of S is equal R of S times G of S over 1 plus R of S times G of S. Okay, now we only need to put in what we have. R of S is 7 and G of S is this guy. Okay, so 7 times 0.7 over S plus 1 over 1 plus the same thing, 7 times 0.7 over S plus 1. Okay, and this is nothing but 7 times 0.7 is 4.9 over, this goes here, so we've got S plus 1 plus 4.9, and this is nothing but 4.9 over S plus 5.9. Okay, so now let's compute the steady state gain, or the static gain of this. K0 is 4.9 over 5.9. Okay, what is this? Where's my, this is always when you change examples on the fly, you need to do the calculation after. 5.9 is 0.83, right? So this is the gain. So we're now reaching 83%. Okay, what are 83% for our input of U equal 2? Well, this is 1.66. So for R, our Y is going to converge to 1.66. Okay, and here we had 1.4, so we improved it. So this was now the fast shot, so to say. You can also do it slowly. So you can say, I'm going to do a limit value calculation for S going to 0 of my new system, which is 4.9 over S plus 5.9. As input, I have this guy here. So it's 2 over S, and I still need to consider that S here. What's the result? Okay, we cancel here, and we let S go to 0. We have 2.9 times 2 over 5.9, and this is going to be 1.66, right? You can take the shortcut here because you know that the step and the s in the limit value always cancels, right? But be careful, if it's not a step, it does not cancel, and this is the source of error. Okay? So, well, this was kind of the things what we have done, yeah, what we know, right? We compute, we have the reference input, we have the output. So now let's say, what do we get? Let's say we actually have an input of 2 and our output gets to 1.66. So the error is 0.34, no? Yes, 0.34. So the question would be, can we compute this via the transfer function? Can we compute this error via a closed loop transfer function? Obviously we can, right? I'm going to write that down one more time. Actually, let's try this. Copy and paste. Nope. Huh. Okay, maybe not. Okay, whatever. I'm going to do it quickly. Okay. This error also shows up in our block diagram, right? We have the reference here, the output here, we have the minus here, and this is the error here, E of S. And we know from R of S to E of S is nothing but our sensitivity function. And we know the sensitivity function is nothing but 1 over 1 plus R of S times G of S. Either you look up in the lecture notes or you compute it quickly. It's not that hard here in this block diagram, right? Okay, so let's do this. What do we have? It's going to be 1 over 1 plus 0.7 times 7 over S plus 1. I think that was it. And if you multiply that out, it's going to be, this S goes to the numerator, and you have S plus 5.9, right? Okay, now let's do the limit value calculation again of this function, which is our reference to the error, okay? S plus 1 over S plus 5.9 times our input were this 2 over S plus S. This one cancels. We let S go to 0. It's going to be 2 over 5.9, and I hope this is going to be 0.34 over 5.9. Yes, this now is 0.34, right? So you don't need to take the detour to compute T of S. You can, if you're only interested in the control error, you directly can compute this control error by the transfer function, right? Obviously, you could say here, my static gain K0 is 1 over 5.9, and my input is 2, right? So you get to the same. Multiply K0 by 2, you're also again here. But this is again a shortcut, so probably forget that one. Okay, so this is how you can analyze pretty quickly the closed loop on paper, right? So, but most of the time it's important to know what's actually happening in a loop, right? I have one last example for today. Yes. And then we are done. And it's actually kind of similar to the first one. We are just taking a look at the different transfer function. So we have our system again, 0.7 over s plus 1, which creates an output. But this time we have an input disturbance, right, to our system D. And we have this controller, which was 7. And we have R. No, we don't need this R at this point. Maybe just confusing here. Can leave that actually. Leave that out. Okay. So, and what we are interested in is the steady state influence of an input disturbance. And let's say this input disturbance now is really just 1 times our step, right? So it's just really a unit step input. So we are now looking at how is our input disturbance influencing our output. Could be for the aircraft, what happens if wind appears, right? It influences our system and it somehow reacts on excites our output. So how is this happening? Okay, and this is what we call the disturbance sensitivity. And we had this is nothing but g of s times the sensitivity function, which was g of s over 1 plus g of s times r of s, right? If you go directly from here to here, it's g of s and 1 plus r of s times g of s because it's the loop. Okay, so let's compute. You just need to plug that in. G of s is 0.7 over s plus 1, and we have 1 plus 4.9 over s plus 1. So if you solve that, it's going to be s plus 5.9, and this cancels and you remain with 0.7. Okay, so we now want to know the steady state influence. Okay, so we say limit s going to 0 of 0.7 over s plus 5.9. The input is 1 over s, right? This guy here. And this s we must not forget. And this one results in 0.7 over 5.9 is 0.118. So the same goes if you compute your steady state gain, it's also going to be 0.8. What that means is a constant disturbance shows up with 11%, 11.8% at the output. If it's a step, right? If it would be an impulse, the steady state would probably be 0. Okay? Does it make sense? I hope so. So really, by that, you can compute pretty simply transfer function. And remember, we actually have ODEs here, right, in the background. We have complicated differential equations in the background. We are simply doing very basic mathematics, which might look a little bit complicated at this point, but basically it's just multiplying, adding stuff, and solving, right? We don't solve a single integral, a differentiating, nothing, right? We're simply doing basic system analysis without solving a single ODE. And this is the advantage of the Laplace domain. Okay, next time we're going to go back to the PID controller, and we're going to take a look for some example system, what these P, I, and D elements are doing to our system. We actually saw already now today, we had a PD1 system and we had a pure P controller, and we were able to get closer to our reference signal, right? So we are actually, this P controller reduces the sensitivity. Unfortunately, it does not get the sensitivity to 0. We will need another element of the PID controller there, and I can already spoiler, it's the integrator. Okay, with that, I'll leave you. I hope it was kind of clear. Stay safe and bye-bye.